Perfect. So today we have Peter Bayer from Autonomous University of Barcelona, who's going to talk to us about evolutionarily stable coalitions. So over to you, Peter.
Thank you so much. And thanks everyone for being here. I'm very grateful for the opportunity to present this paper. As I said a minute ago, it's the first time I'm presenting this paper. So a lot of things are very much in progress, particularly my introduction. But you will see in a bit. Let me get started. This is basically the introduction. I won't give you much more. I'm starting off with two premises. First one is humans work in the interest of the group a lot. Not just humans, but of course, I'm going to focus on humans today. And the second premise is that humans evolved through natural selection, where the unit of selection is the individual. And a lot has been said about these two premises, but I'm trying to make sense of it. It's not to say I have to make sense of it, uh, but I want to have a model specifically around this, and you will see what I mean when I say specifically around this. I want to have a model without some extraneous factors. Okay, but first of all, let me talk a bit about what the interest of the group is, because already here we might have some controversy. When we take any strategic interaction between n individuals, it is easy to describe coalitional behavior because we kind of agree that it means coordinated actions by members of a subset of individuals. And we already agree on what the subset of the individuals is, what a coalition is. Okay, I just take a subset of the player set. But to define coalitional interest, we have already started branching off into various ways that one can do this. And I'm going to keep it very simple. I'm going to describe what I call a cooperative approach and what I call a non-cooperative approach, just to give you a taste of where some sources of controversy can come from. And after that, well, even now, I'm going to argue that having an evolutionary foundation of what coalitional behavior is, that is an action, a coalitional action in the service of the coalition, is even harder. One of the ways that you can do this is that you have to assume group selection. This is a very classic argument, also very controversial. Or, as Johnny does it very well, you have to assume the existence of some sort of collective gene, and you can show that this collective gene prevails. But it doesn't really speak to what a coalitional interest is. So let me show you what I would call the non-cooperative version of coalitional interest or group interest. Just the basics. I have a normal form game, U mapping from the strategy space to R to the power of n is the finite set of players, X is an action space, Xi, the actions of player I, and U is the game. Then I have a status quo X, an action profile, and I have Y sub C, which is just a designated action profile for members of this coalition, C that is a subset of N, which I forgot here. But so then we say a coalitional move is just me taking the game from X to YC, X minus C. So I'm changing the behavior of everyone in C to this YC. And then you might say, if you're a rational player, you would only make such a move if that move is beneficial for you. So individually, your payoff doesn't decrease from this. Okay, so that's one way of defining the group interest. And then, of course, we have an equilibrium concept that accounts for this. It's called the strong Nash equilibrium. An action profile is a strong Nash if there is no such coalitional move away from it that would be collectively rational in this sense. Okay, so my short argument here is that the strong Nash and everything that's based on it imagine coalitional interest as some sort of intersection of individual interests. Okay, existence is an issue. This is going to be a common factor whenever you're talking about coalitional deviations. You're going to meet this hurdle that it just might not exist. Okay, in particular, strong Nash may not exist. Here's an example. I have the classic prisoner's dilemma. Cooperate defect with these payoffs. The only Nash equilibrium is the defect one, but it's not strong because the players can together decide to deviate to cooperate. So the only Nash is not stable for coalitional deviations, so there is no strong Nash in this game. Here's a game where a strong Nash exists. In fact, here I actually select. This is the classic stack hunt game that we all know. Hare, and stag are the Nash equilibria. But hare is not strong because we can just both agree to hunt stag, and there is no way out of stag, individual or coalitional. Okay, and I'm going to talk about, for this paper, it's going to be a little more relevant to talk about the cooperative way to define a group interest. And for this, I'm going to go back to the basics and define transferable utility games, especially for me, because I for sure need a reminder. Maybe you do too. I have a transferable utility game characterized by some function v that maps from all subsets of the player sets into the real numbers. And in this framework, v just tells me how much each of the coalitions is worth. Okay, it's not saying anything about the individual values of the so how the coalitions are supposed to divide those values yet. It's just saying how much they are worth together. Okay, this is a classic example. I have 3 players. These are the individual values. If player 1 is alone, he's worth 1. If player 2 is alone, he's worth 2. Player 3 is alone, is worth 5. So the way we interpret this is that on their own, the players are able to achieve whatever their value is. In pairs, if 1 and 2 team up, they're worth 10. 1 and 3 team up, they're worth 15. 2 and 3 team up, they're worth 20. If they pair up in these particular ways, they're able to achieve this value. And of course, we have the last one. If they all work together, they can achieve, in this case, 30. Okay, the focus of cooperative games is not necessarily what people do, even though I say they team up or they come together or they deviate. These actions are actually suppressed in this notation. What we are looking at most of the time is how much they should get from a fixed pie. So I'm not trying to predict how these guys behave. I'm trying to come up with how they should divide the pie being the total value of the grand coalition where they all work together, such that they're all happy in some sense, or that the division is fair, and so on. Okay, so bringing it back to group interest, assume that I have some sort of social planner, and the social planner decides on an allocation. Okay, gives player 1 phi1, player 2 phi2, and so on. And the question that we pose is that will the individuals and the coalitions be satisfied? And we assume that if everyone is satisfied, the players stay together. Nobody's going to try to block this division. Nobody's going to go on the streets and protest or do something else. If someone is unsatisfied, whether individual or coalitionally, they will leave and the group will break down. So then we can assume that this allocation is in trouble. But we don't really model what happens when they leave. We're only interested in whether the coalitions are all unsatisfied or not. And unsatisfied here means that the sum of their allocations, so how much everyone gets from the social planner, is it bigger or larger than the coalition's worth? If the coalition's worth is larger, then this coalition says, no, I don't like this allocation. We're going to leave. We're going to create this value VC together. And we don't really care how they divide it. We just know that this phi is in trouble. Okay? The bottom line for me here is that coalitional interest is now expressed as total worth and is compared to total rewards when the rewards are this sort of allocation. Okay? So the difference between the cooperative and the non-cooperative here is that the non-cooperative was individual rationality for a coalitional deviation, and the cooperative was some sort of collective rationality where there is not even an individual condition here, right? There is no individual participation constraint. It's the group together decides, in a sense. Okay, yeah, and of course, if you know cooperative game theory, you know that this gives rise to the core. Okay, this is an equilibrium concept capturing stability against such coalitional deviations. An allocation is said to be in the core of the game V if every coalition is satisfied. And crucially, as we mentioned this in the last slide, but we cannot divide more than the worth of the grand coalition. Okay. Utility is transferable means that any unsatisfied coalition C could leave and distribute the worth in any way that would dominate the original allocation by the social planner. Non-emptiness of the core is, of course, an issue as well. And there are several results that I don't know too well that describe in what case or characterize the cases when the core is non-empty. Okay, quick example. This is a game where the core is non-empty. This is the original game that I showed you. 1 is worth 1, 2 is worth 2, 3 is worth 5. These are the pairwise values. This is the total value. And if I divide the grand coalition equally, everyone gets 10. That happens to be in the core. Every coalition will be satisfied. The funny part here is that the players are clearly not equal here, right? 1 is worth 1, 1, 2 is worth 10, whereas 3 is worth 5, 2, 3 is worth 20, but they get the same. Okay, but even so, no coalition can team up and block this, or no individual can team up and block this. Here's a classic case when the core is empty. This is the same as the last game. Everyone is individually worth the same, 1, 2, and 5. But here, every coalition is worth the maximum of the individual in it. So 1, 2 is worth 2 because the largest individual is 2 and he is worth 2. 1, 3 is worth 5 because 3 is in it and he's worth 5. 2, 3 is worth 5 and they together are worth 5. This is called an airport game. And I think it's named after the fact that how long do you have to build a runway depends on the longest or basically the largest aircraft that you put on the plane, on the runway. The story doesn't matter too much. This clearly has an empty core because for us to be in the core, we need to satisfy each individual. So we need to give player 1, 1, player 2, 2, and player 3, 5. That is more than 8. That is sums up to at least 8, which is larger than the value of the grand coalition. Okay, so core is actually frequently empty. Okay, what am I talking about in this paper? Because this is not really what I'm talking about. This is just all providing motivation as to why coalitional interest is interesting. I'm trying to build an evolutionary model capable of tackling coalitional actions. And the two main ingredients that I will use is assortative matching or kin selection, and what I will call heterogeneous interactions with active and passive actions. I will make this more explicit. I will present you some results. One is that evolutionary stable strategy will prescribe stability against coalitional moves. So if I wanted to phrase it in a more fancy way, coalitional action will evolve, group interest will appear rather than individual interest. And evolutionary stable strategy will prescribe some core allocation of an appropriate TU game. So if the question was, is the non-cooperative or the cooperative coalitional interest the result of evolutionary stable strategy? The answer is it's the cooperative one. We will have group interest being total interest of the group rather than a set of individual participation constraints. This is clunky, but you will see. And for this, you will have to see the rest of the paper to understand maybe. But when I say appropriate TU game, it means that I have to be a little bit tricky about how I define the coalition's worth in those three TU games. It will be some expected value where I take into account coordination failures within the coalition. I will make this very explicit, but this is just setting it up. And as a side note, the rate of successful coordination, so when I'm taking into account how frequently do coordination failures arise, the rate of a successful coordination will be equal to the rate of assortative matching, which again is something that I will define soon. So I'm not assuming group selection, I'm not assuming any cooperative genes. The results are all driven by this ability to pass on these passive genes in a heterogeneous interaction. It's a good time for questions if you have any, but I'm not sure if I see if you have hands put up, so you can just interrupt for this. If not, I am more than happy to jump into the model. So for those of you who are blessed with the knowledge of the previous paper of mine, the model is the same. Infinitely many individuals will interact in groups of n, countably infinite. Individuals will be born, they will be put into these groups, they will interact once to receive evolutionary fitness, they will reproduce according to that evolutionary fitness, and then they will die. This is just a background story. I'm not going to model this. Because I'm interested in evolutionary stability, my model will be entirely static, and this is the dynamic story that produces it. Interaction is heterogeneous, which means there will be roles in the groups. The roles are described by a set of types. And I will make this explicit later. But for now, the set of types is just a finite set that goes from 1 to n. Once I sort n individuals into an interaction group, each of them will receive a type. And in fact, each type will be assigned only once. That type tells me everything I need to know about that player in this interaction group. The type will encode what kind of actions the player can take and what the payoff function that player faces in the interaction game is. Otherwise, the interaction game is just a non-cooperative game, something that maps from the set of actions to the set of real numbers for each individual. And the notation is basically the same as what you're used to in non-cooperative game theory. Now, the trick is that individuals are born with strategies that determines their action in every possible type that they can be born to. Okay, so you are born with a strategy x1 to xn. Then I assign you to an interaction group. You will be with n minus 1 other players in a group of n. And then you will get a type. You will get type I. Then you will select the ith component of your action, your strategy, and you're going to play that action in that interaction group. I call this the active action and everything else is passive. Okay, I will have an example. N is an arbitrary finite number, and the action space for every type is yes or no, 1 or 0. And the game is, I call it the heterogeneous threshold public goods game. So 1 encodes contributing to the public good and 0 encodes not contributing. So here the game is, if at least T individuals in the group contribute or participate, so the sum of the individual's actions is at least T, then every type will receive some reward Wi. And this is where the heterogeneity comes in, because this reward can be different from player to player. And the participation costs are also heterogeneous. If you are in type I, participation costs you Ci. Okay, so we have 2 to the power of n strategies. Every type can participate or not. And what we notice is that the set of types equals the set of players for the normal 4-game U. And the action space of U, so what kind of actions can happen in this non-cooperative game, equals the strategy space of the evolutionary game, right? Because every strategy has to encode what you play as every possible action, as every possible type. Okay, this game is X antisymmetric because everyone can be any type with equal probability. So in the end, this is going to define us a nice symmetric evolutionary game. But X post asymmetric, after I assign the types, the payoff functions are very, very different. Okay, this is my visualization. For now, let's stick with 2 possible strategies that are competing in the population, black diamonds or white diamonds. Here, 1 in 4 are white diamonds and 3 in 4 are black diamonds. And these are my players. These are my strategies, sorry, my individuals who were born with these strategies. And the squares are the interaction groups. So now we're playing in groups of 4. And the circles are these numbered types. Okay, so these groups are waiting for the players to occupy them, and each player can find himself or herself in any of these types. And then they play the interaction game, and what they do in the interaction game is all already encoded in the strategy. Okay, crucial component of the model is that group formation is not by uniform sampling. Identical strategies are more likely to meet. And this is encoded, this is modeled by assortative matching. If I have a distribution of 2 possible strategies, X and Y, and the distribution is this Q, Qx, Qy, Qx plus Qy equals 1, then the probability that if I am a strategy X, and I'm sitting in type I, the probability that I meet another strategy in my group in type J who is the same as me is more than Qx. It is R plus 1 minus RQx, where R is some parameter between 0 and 1. Okay, the probability that I meet a different strategy than me, so Y, assuming that I am X, is 1 minus R times Qy. This probability R, I definitely encounter genetic copies of myself in this group at any type. Okay, I'm only interested in ESS, so I'm only defining the matching process in the limit where there's 2 strategies. In fact, I could just define it in less. And Alex's Janssen and Rigo's paper shows that such a process exists. So I'm not cheating here. even though I'm silent on what this matching process looks like for any other situation. For the limit when there is only two strategies, I want it to do this.
Just to clarify, is there an independence assumption here about?
Yes.
Okay.
Yes. And I think Ingela and Jürgen's paper 2016 shows that I think you need both of these papers to show that such a process exists. But yes, the types there is independence in the limits. Okay, if R equals 0, then interaction is uniform at random. I'm interacting everybody based on just how frequent they are in the population. And if R is getting close to 1, I only interact myself, right? I only interact with strategies that are exactly like me. And for in-between values, of course, we have some sort of combination, which is exactly the point. Okay, so this is the key component of the model. How to visualize this? If you assume R being reasonably high, and we have this frequency distribution where the black diamonds are 75% and the white diamonds are 25%, after everyone has been sorted into groups, if you are the white strategy, you can still perceive that the majority of your opponents are also the white strategies. And if you're the black strategy, chances are you're going to find yourself in interaction groups where there's even more than 75% of the population has the black strategy. Okay, that's the only thing that's happening here. Right? If interaction was uniform at random, basically all the groups should be like 1 white diamond and 3 black diamonds, and that's not what's going on under high assortativity. Okay, after I have given players interaction groups, everyone's been sorted into types according to this process. Then I award payoffs and I calculate evolutionary fitness. And this ugly thing here, don't worry, it's not going to be on the test. It just means that if I'm trying to evaluate the fitness of any strategy, all I do is take an average of the interaction payoffs of anyone with that strategy across all the possible partners that they can find themselves with and how much that gives them, of course. And of course, I'm going to have to average it over all the positions that they can find themselves in. So there's two sums here, basically. One is across types, and the other is this ugly thing, which tells me how likely am I to meet any other strategy combination and how much I get if I meet that strategy combination. Okay, you either see it or you believe it. For now, let's believe it. Okay, and then of course I'm looking at evolutionary stable strategies with the static concept dynamic story. I have a resident strategy, which is basically the entire population. Its frequency is very close to 1. A mutant appears, and I'm asking, does the resident outproduce the mutant? If for any mutant, the resident outproduces the mutant, then it's evolutionary stable. Okay, this is the way to put it formally. I have a resident and a mutant, and I look at the limit. A resident X is stable against Y if the fitness, given that the frequency of the resident is 1 and the frequency of the mutant is 0, the fitness of X is larger, is at least the fitness of Y. Here I'm being lazy and omitting the extra condition, what happens in the case of equality. I just say that the strategy is evolutionarily stable if it's stable against all possible mutants. Okay, we gotten through the model. Let's see what happens. So the main result is this. I have two strategies, and I'm denoting by C the maximal coalition where the strategies are different. Okay, so C is all the types where Y is different from X. It may be that Y is different from X in every type, in which case C is N, but it may be smaller. In any case, I'm going to call C the set of deviators. And this is just a notation for any X prime and a subset of N. I'm going to write US X prime as the sum of the utilities that we get if everyone in the game plays the strategy corresponding to XY, X prime, and U minus X will be everybody else, everybody not in S. So then, a strategy X is stable against the invasion against Y, if and only if, again, I'm ignoring the case of equality for the presentation, for the paper, we do it properly. And here is what's happening. I'll just let you absorb this for a second, and I explain it in a little bit more detail. This thing kind of looks like a probability of the subset S, subset C, being deviators, where R is the rate of assortative matching. So I'm taking R to the power of S, 1 minus R to the power of C minus S. And then I'm looking at the payoff advantage of what happens if this subset S deviates. Subset S successfully plays the mutant strategy or the mutant action. Everybody else didn't show up for the party. And I'm looking at what the payoff advantage of these guys is. Plus R times what I call net externalities minus C. These are the guys who are playing the same thing as in the resonance strategy. The total payoffs of what happens to these guys if S deviates minus the original payoff. And I'm multiplying everything with R.
Good.
Okay, and then I'm taking this weighted sum for every possible subset of the set of deviators. And that's what matters. If this is negative, we are stable. If it's positive, then Y invades. So what we get is basically some expected altruistic coalitional value with independent absentees. The altruism comes from this, because I'm taking into account my externalities. And it's a coalitional value with independent absentees, where being an absentee means I wanted to deviate. My action is different in Y than in X. So I'm part of the set C, but I still may not be able to show up for the party. Okay? And each subset of C, S, can end up being a mutant. And this is the probability of that subset being a mutant.
Can
Just
you explain what
Detecting
you mean by showing up for the party? Like,
Pardon me?
can you explain what you mean when you say showing up to the party?
Yes. So let me unpack the metaphor, and then I will go back to the formula.
Yeah, this seems
I'm
like a very
inviting a bunch of
important slide.
exactly. No, we should talk. If we don't move any further than this, I'm fine. That's the only result that I find crucial to talk about. So I'm inviting a bunch of people over to my place. Let's call this the set C. Okay, the resident action is not coming to my place. The mutant action is coming to my place. C is invited. And what happens basically is that everyone has some show up probability. Okay, I invited Johnny, I invited Alex, I invited everybody, and everybody flips a coin, which is heads with probability R and tails with probability more minus R. If it's heads, they come. And then we have a party and we have this payoff advantage, right? With the players who successfully deviate, who come to me, then we have this payoff advantage in total. And I'm taking an expectation over all of this. Plus, I'm adding these externalities. How would everyone who I didn't invite feel about this party, depending on who ends up showing up? And we take them into account with this extra factor R.
What's the justification behind this random showing up or not? It's...
So I'm going to do a proof by example thing.
Okay. And just before we move
Where I
on, that's
will,
not maximal. Is that meant to be minimal? Because I think if it was maximal, it'd y would
maximal.
equal, if you let C be everyone, then y would equal YC, right?
No, I believe it's the maximal coalition. So from Y, you're just looking at what is the largest set C such that
Y equals YC.
Y, Y, oh yeah. Wait. YC is different from XC,
Yeah, that's true.
right? So for any
Yes.
subset of C is also a coalition such that this is true. That's why I'm taking the largest such coalition.
Um,
So I think what Jonathan is saying is that if you take C equals the all everybody, then it just says that Y is equal to Y in that case. And that's true. And so you could see take
Yeah.
be everyone.
Uh,
So that's what we don't get.
Okay, maybe I'm lazy with this definition. From X and Y together defines C. That's what I'm trying to say. I'm taking a strategy and I'm taking another strategy. I'm looking at all the coordinates in which Y is different from X. And all the coordinates C, I call them the maximal coalition such that this is true.
Yeah, I
Yeah.
understand. I just think if you put minimal there, then you get what you want. Maybe
Yeah.
counterintuitively, linguistically, but it's all the ones you have to change to be equal to Y. Otherwise, those two things are not equal. But let's proceed. Can
Okay.
think on this.
So just to show you some simple cases of what this implies, if C is a singleton, that means the difference between Y and X only appears in one coordinate. In this case, that coordinate is I. So only one type changes. Then this Y invades my X, if and only if this weak inequality. If this is true. Okay, so the payoff advantage of the type that deviates plus the payoff advantage of everybody else together times R. It has to be No, this is actually true. This is a strict larger than or equal to 0. Then we have an invasion. Okay, so this is a variant of Hamilton's rule. The strategy is ESS if and only if it's a Nash equilibrium of the game that I define like this. Okay, I define this game U tilde for every I and every X as the original interaction payoff that I get if everyone plays X, plus R times everybody else's payoff. Okay, so all ESSs are altruistic Nash equilibria in this model, where the rate of altruism is R. Okay, so this little thing is this monster, just for C equals the set I. Okay, here's another small example, or small, but already quite large. If C is a pair of players, so I and J are changing their behavior. So the mutant action, so the mutant strategy is YI, YJ, and everyone else plays X. The stability of X versus Y reduces to this thing. This thing is what? R times how much we get, I and J gets, or how much payoff advantage they get from this deviation, plus R times everybody else's payoff effects if I and J deviate, right? And here we have this 1 minus R times what if only player I shows up for the party and player J does not? So player I deviates, player J plays X. What is the payoff gain of player I? That's what we see here. And then we have, what if player J shows up and player I doesn't? What is the payoff advantage of player J in this case? And then we have the externalities, 1 minus R times R. This is the externalities if only I shows up for the party. And this is the externalities if only J shows up for the party. Okay, what we get here is that the pair designs jointly, they anticipate this coordination failure, and they're altruistic. This is not a strong Nash condition, because a strong Nash would prescribe something individual for both I and J. But here, what we see here is one condition for both of them as a pair. There's no individual participation constraint. Okay, should I do the example? And then we will go back to the monster
Yes, I think.
to see what happens. Okay, so take this heterogeneous public goods game. Okay, n equals 4. We have 4 players. For now, let t be 1. So one player can already form the public good and can give everyone the benefits. And I'm just looking at what is the invasion condition. When does this 0, 0, 0, 0 strategy get invaded by the 1, 0, 0, 0 strategy? Okay, as type 1, this player will contribute. As types 2, 3, and 4, the mutant and the resident both don't contribute. How do I calculate the resident's fitness? So the resident being the not contributing strategy. If I'm a resident and I get sorted into any type I, anybody I will meet will be like me, basically, right? Because my frequency is almost 1. So this conditional probability X conditioned on X equals to 1, or is very close to 1, if we're being precise. So as an X player, I will never meet any mutants. virtually never. The public good doesn't get created and there are no costs. My payoff is just 0 as the resident. Now the mutant is trickier. If I'm the mutant, if I get sorted into any type I, any other type J will be occupied by a mutant with probability R. This is because mutants are rare. This is basically 0. So I have R plus something very close to 0. That's basically R. If I'm a mutant and I get sorted into type 1, I will contribute and the public good will be created, no matter who I meet. The other types play the same thing anyway, residents or mutants. So my payoff is just the gain minus my cost. If I get sorted into any other type, I will play 0, because this is just what I do in any other type. With probability R, a mutant will be sorted into type 1. And that's what I'm interested in, right? Because only in type 1 do the mutants contribute. With probability 1 minus R, a resident will be sorted into type 1, and nothing happens. But if a mutant gets sorted into type 1, they will contribute, and then I get R times WI in expectation, right? I get WI with probability R. This is what this means. So in total, the mutant fitness will be just 1/4 times what happens if I get sorted into type 1, plus R times what happens, this is what happens in total if I get sorted into 2, 3, and 4, which is just R times W2, W3, W4. So this invades the resident as long as the gain of type 1 plus the gains of every other type times R are larger than the cost for type 1. Right? This is how altruism ends up being relevant, because I don't care about just the comparison W1, C1. I also care about how my co-players get affected by my action. Okay, this is a simple case simply because T was 1, and we didn't really talk about coalitional actions yet, but this already demonstrates how we calculate fitnesses. Okay, so let's spice it up. Now T is 2. I need at least 2 types contributing, and I'm interested in when does the never contribute get invaded by the type that contributes in the first 3 types and doesn't contribute as the 4th type. So now I have 3 deviators, 1, 2, 3. If the mutant ends up being sorted into C, so I am either type 1, type 2, type 3, in order for the public good to be created, I need to see at least 1 more mutant in the types C that is not me, right? If I am in type 1, I need type 1 or type 3 to be occupied by a mutant, because then they contribute, and then the public good is created. If that doesn't happen, if both of them are occupied by residents, then they won't contribute, and I'm wasting my breath for nothing. I'm just paying the cost and I get no benefit. Okay, so the fitness is R square WI minus CUI. This is the case when both of them are mutants. In fact, that happens with probability R square from my perspective. Then we have 2 times R times 1 minus R. These are the cases when one of them is a resident and the other is a mutant. That's okay. The public good still gets created. And this is the case when both of them are residents. And then I'm sad. I'm paying the costs. and the public good doesn't get created. Okay, this was when I was a mutant and I was put in one of the 3 deviating types. If the mutant is put into 4, then it needs to see 2 mutants for the public good to be created. Okay, if the mutant was here, it only needed to see 1 more. Here it needs 2. Because even though I'm a mutant here, I happen to be in type 4, where I'm not myself contributing. So my fitness, for me to get my reward, I need to see 2 other mutants. This is the probability where everybody is a mutant. Type 1, type 2, type 3. That happens with probability r to the power 3. Then I get my reward. If 2 of them are mutants, I still get my reward. And 1 of them is a non-mutant. 1 of them is resident. This is when 2 of them are residents and 1 is a mutant. Then I don't get anything. There is no reward, but I also don't pay costs because, right, I'm still not contributing. And here is where everybody is a resident, except me, but I'm not contributing either. Okay, so if the mutant is sorted into a non-deviating type, then 1 more mutant is needed in this sense. And this is why we get that extra R in the case of altruism. Okay, summing everything up, I just collected all the terms based on R's, and I'm multiplying by n because even though we are taking an average, I just don't want to carry the 1n everywhere. So this is what we get. And I'm going to unpack this brutally because here we had everything summing up based on types, but we can sum up based on who shows up for the party in my parlance. Okay, so I get all of them showing up for the party. That happens with this probability. This is the total payoff effect for everyone who shows up, and this is the externality. This is what happens if 1 and 2 show up and 3 doesn't. Again, total payoff effect for 1 and 2, externality for the one who never was invited, and so on. Okay, and if you are really fast, then you see that this thing is indeed equal to this thing, and this thing is actually the same format as the original monster. Okay, I know this is just an example, but basically the proof works the same way, which is why I don't even show you the proof. You can just organize everything such that it is indeed this weighted sum with the probabilities, the total payoff effects, and the externality. Okay? And I have 5 minutes to sort of wrap everything up. I'm not sure if I can, but I will pause here if you have questions right now. If not, I will just continue and try to make it fast. So I'm trying to formalize this sort of who shows up for the party in the terms of a cooperative game. Okay, so forget everything, starting from scratch. I have a TU game V, and I have a parameter P between 0 and 1. And I'm going to define the Bernoulli extension of this game as this. Okay, for P, the value of C is just an expectation of who ends up showing up for this coalition. Okay, where each coalition member individually shows up with probability P. Okay, that's all that's happening. And now, thinking back to the evolutionary game, what if I can have this VS express the fitness gain of the coalitional move? And this is what's going on. We don't have time to analyze it in super big detail, but this is just me given a status quo X and an alternative. These are just two strategies. For any two strategies, I can just define a TU game where X and Y end up being sort of, so the game ends up being dependent on these two strategies. And for every subset of N, I'm defining the TU game in this weird way. Yeah. Which weird way is something that we're familiar with already. So this is just the payoff gain of the subset S if they all deviate from X to Y. And this is R times the externalities on those who didn't even want to deviate. If I take the Bernoulli extension of this game, of this TU game, I will get something that is exactly equal to this fitness difference. Okay, so what we did is express the value of the coalitional move in this weird TU game way. And we did it from a status quo X to some designated alternative Y. And next, for every possible Y, I'm going to ask, what would that coalition do? Right? If that coalition C would be free to pick what they do, instead of moving from a designated status quo to a designated alternative, I'm just asking, what would they move to? What is the maximum fitness gain that that coalition can achieve? Okay, so I get another TU game by taking a maximum over all possible strategies for coalition C. Okay, so members of C deviate optimally. Then I will do one more trick, and then I'm done. Express it as a coalitional gain under the optimal deviation. So I take this maximum gain and I just add UC of X for each C. And I get yet another TU game, this pre-index X W of C is just going to be another TU game that I have derived from the evolutionary game, assuming some status quo X. And then the claim is that an ESS has to be stable against all deviations. It's the same as being stable against all maximum deviations, which is the same as this game having to give each coalition at least UC of X, the sum of the individual payoffs. And that happens to be a core condition. So the ESS will have to produce fitness values that are in the core of this tortuously obtained game W. And that's basically the result. An ESS has to produce fitness values that are in the core. In the limits R equals 0, there is no coordination, and the types behave as if they are fully selfish. So the ESS just reduces to Nash equilibrium. In the limits, R equals 1, coordination is certain, and types behave as a fully altruistic. ESS is just a utilitarian efficient strategy. This is what happens in the limits, and everything for an in-between value of R is just the core of this weird cooperative game. Okay, and miraculously, I might finish on time. This is just recapping the results. So we have assortative matching and heterogeneous interaction. Coalitional action evolves for any game, for any U. Coalitional interest is now endogenously obtained as this total expected coalitional value with independent absentees and altruism. Okay, it's quite a mouthful. This is just referring to that monster equation that you've seen. And checking for ESS, if I have a candidate strategy as an ESS, to check whether it is an actual ESS, is equivalent to checking whether the payoffs that it provides is in the core of some appropriately chosen TU game. And at the limits, we have some nice behavior. It's somewhere between Nash and utilitarian efficiency. Okay, I have some more things to do, but my time is very much up. And I'm very, very grateful for your attention. And feel free to ask questions.
Okay, thank you very much. I'll stop the recording and we can move to some discussion.